Okay. Now this should stream to the same link that's already set up. Okay. All right, seems to be doing it. Now this should stream to the same link. Okay, so that seems to be on. And now we'll hopefully be able to get the other things working. Okay. All right. Right. Okay. So for group A, what you'll do, I'll just show the screen here and you'll be able to take your attendance. It's a little bit different. I don't know what other option we have though. So let's see here. Okay, that's working. I'm going to see if I can share my screen. That should do it. You probably see more than okay. I think I got it working. Okay, so welcome everybody. Thank you for joining us today. We have the opportunity to meet virtually because of the weather in New Jersey, and this is for Group A. Group B is also going to meet virtually, and you can go to the breakout rooms. So there are two breakout rooms, one for those who are in DSV and one for those who would be actually in the virtual section. So those breakout rooms are there. Okay, so there's a question in the chat about what needs to be done for Group B's attendance. Group B doesn't have attendance, or whenever you're in the lab, there's no attendance. Just the lab assignment needs to be submitted within about 40 minutes of when that lab time ends. So that's kind of quote attendance. And of course, you could do it earlier or you could not go to the lab, but the TAs are there to assist you. So that's what I guess is happening with the attendance for Group B. Okay. There's attendance on 211. Yes, that will happen. That should become available when you meet in the fiber optics building on 211. Okay, so today's just Group A attendance. All right, so let's go ahead. Unless there's an issue, I could have had an issue with the dates. All right, but that should open up on the 11th of February for Group B. Today, Group A has their attendance. All right, so any other technical administrative questions in terms of what we're doing? Okay. It's a little bit different, but since we're all virtual, I'll just say that if you want to take attendance right now, and if you're in Group A, this is the screenshot that we're going to have. So it's just the boring white background. But of course, you'll be taking this screenshot with Zoom. So I'll hold it there for a minute while people might take screenshots, and then I'll be able to also show this later at the end. Okay. Sure, you could. I guess that's gotta be right. So take the selfie, yes, with take the shot of the literal screen. If it's not, it's a little bit different, but then yeah, with the selfie in it, that's correct. Okay. Excellent. Oh, okay. There's an issue with the title. Okay, let me see what has transpired with hold on. I see now there. Oh, no, 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 no. That's not supposed to be there. Okay, so let's see here. We will go ahead and look at Canvas just to make sure we got things straightened out. Okay. And, so today we have our attendance, which, okay, yeah, that's the reason. Okay, sorry. I just didn't put the right date in there for Group B. Yours will be due on, this is going to change over to the 11th. Okay. All right, great. So Group B, you should be straightened out. Group A, I think you got it set up. Okay, so let's get going. Administrative details worked out. Please feel free to put the comments in the chat. I'll try to get to them as we go through. This is, a flashback to times where we did things in Zoom all the time. So today's class is going to focus on a transition from thinking about particles in gravitational fields to thinking about them in electrostatic fields, or thinking about them using kind of potentials that would be associated with molecular interactions. So we're going to look at collisions between, or interactions between electrons and interactions between atoms. We'll discuss how we think of these interactions from the mathematical perspective, and then, of course, we'll get into how we approach simulating these interactions, both the electrons that are charged and atoms which are going to be in a special type of a conservative special type of potential called the Lennard-Jones potential. And then Group A, we didn't really get a chance to talk about bubbles and how bubbles can also be thought of as particles. So we'll get to do that near the end. I'm not quite sure exactly how much we're going to get through today. It kind of depends on questions and the interaction that we have in this virtual environment. Nonetheless, we should be able to get through everything. But if we have questions, let's take a moment and talk about them. So there are a couple questions or big concepts that we want to be able to take away from today's class. One might be, what do these techniques that we describe allow us to model or simulate? And how do we model molecular collisions and interactions? Now, when someone in the class asked that question of, okay, particles that are interacting with each other, can we think of them in the thermodynamic context, or the context of thermodynamics? And we said, yeah, we can think of them in terms of gases. And in reality, you can think of them in terms of the interactions that atoms have, or molecules have, in solids as well. We're going to continue our path to build up from these fundamental principles of how particles interact with each other to starting to think about how molecules could interact with each other. But then we're going to take a jump the next time we meet. We're going to talk about how it doesn't really make sense if you're going to talk about, for example, how temperature is changing in a heated block, to run the simulations from the molecular perspective. It's going to be too slow. But what we're talking about today is interesting and is relevant to a lot of different fields of research, where you are looking at maybe a process in semiconductor processing. Okay, that's repetitive process, and where you have maybe atomic layer deposition, or you're putting down angstroms or nanometers of a layer of material. And so this type of simulation is often employed by many people when they're interested in kind of nanoscale type effects. Nonetheless, for many practical engineering applications, we're going to move on to finite difference, finite element, finite volume types of simulations, and it will be kind of a new framework. We've talked in the past about the discretization involved with simulations in terms of the space, in terms of the time. We are, for the most part, still thinking about discretization only in time. But the next time we meet, we're going to start talking about discretization in space and time. So that's just kind of a little foreshadowing of where we're going. When we think about particles, what are the mechanics that we might employ when we think about their interactions? And we've kind of talked about this before, but if you like, go ahead, put some things in the chat, and just kind of share. Okay, what kind of things have what kind of interactions would you be interested in capturing? What do you think? Or what? Okay, electrostatics. Excellent, right? That's absolutely correct. Okay. Ionization. Oh, okay, sure. Okay. Yeah, so you could think about charge in terms of, okay, not just like two electrons, not just two atoms, but maybe you've got some type of molecule, or you've got a larger particle that's made up a bunch of these molecules. And now, they develop some charge. Okay, so momentum, yes. So we want to preserve momentum, right? As we use the Verlet integration method, or as we use the Euler method, we want to say, okay, these particles are marching along. And with the bouncing balls, you've got some ideas already about how you can think about making sure that from one time step to the next time step, if there's not an obstacle, you keep that momentum. But if you hit an object, right, you're going to bounce off. What's interesting today is that, well, might be interesting to some, is that we're going to actually use some techniques that don't employ thinking of these particles as having a hard surface. So we can conserve momentum. Nonetheless, we're going to think about it not in terms of, okay, I hit like this, the boundary of one particle and the boundary of the other particle, they interact at a certain angle and they bounce off. We're going to see that type of behavior, but we're going to use these different potential functions to generate those forces. Okay, excellent. So yeah, you could think of magnetics, you can think of gravity, right? These are different things that between particles that we can think about, right? So those are thank you for those comments. Now, as we place our particles relative to each other, and as we think of their interactions, we can place them in conservative potential fields. So gravity is, for example, a conservative potential field, where we know that if there's no drag on the particle, I can get this nice conservation between the kinetic energy that I have, right, 1/2 mv squared, and the potential energy that I might be experiencing. And so this gravitational potential can be written as we've written it before, the minus g times the product of the masses divided by the distance between them. And then this is something that we can describe for any system that essentially has these particles. Now, the force that we end up thinking about between these two particles, that comes from the negative of the gradient of this potential field. Okay, and so we go from something that we can think of as having this field quality, this essentially scalar quantity as we go around in our space, okay, to vectorizing it, by taking the negative of the gradient. And gravity is going to always attract the two particles to each other. So this might be a little bit of foreshadowing, but if I'm not going to think of the particles as kind of being solids that can bounce off of each other, what is going to, how can you think of modeling this kind of bouncing effect? And that's something that we're going to talk about today. And one approach might be to, if I'll skip this one for a second, one approach might be to say, oh, I can have a repulsive or an attractive force, right? If I change the charge, right? Change the sign of the charge on the particle. Okay, so that is one way to say, oh, these particles are approaching each other. Maybe they have momentum, all right, or maybe gravity's pulled them together. Maybe you have gravity and electrostatic charges, but you're going to probably have to have with the charges often that those forces can be higher than gravity. So when you have two particles that interact with each other, if you want them to bounce off of each other, you could assign them opposite charges and then use these electrostatic relationships if you want, right? Again, negative of the gradient of the potential involved between two charges. You could think of springs also as causing some bouncing. The thing with springs, though, is that you'd have to somehow shut them off, right? So let's say that you had two, I had two particles coming in close proximity with each other, and the whatever when I go past equilibrium, I'm able to now get this compressive stress in the spring, right, or compressive forces that then push the particles away. Well, as they go past that equilibrium point again, then they're going to get pulled back to each other. So maybe, I had to do something clever where they come in toward each other and they get pushed out and then they get knocked off. All right, because I cut off the springs or something. So springs are interesting because that's kind of, an oscillating network that'll go back and forth. With these electrostatic charges, we can kind of place some of these different variables and charges in place with each other. And for the assignments, you'll be given these values, so you don't need to worry about them too much. But no, so okay, so someone has requested that this go to the cloud. This is actually being streamed to YouTube, so I think I can deny that request, and it'll just be on YouTube in the link that I think I posted in the assignment, or in Canvas. All right, sorry, distraction, squirrel. All right, so we can think about the variables and the parameters to get them, a sense of what the magnitude of these forces will be. And when we do that, we can observe some interesting behavior, and we'll do some of that in a minute. All right, just hold on. With molecules, we have an interesting opportunity to think of potential functions that can be both attractive and repulsive. So here we are saying that, okay, it's kind of attractive or repulsive, but you can begin to think of a potential function, maybe, all right, that at far distance, for example, at large, when the particles are far apart, the negative gradient of that potential is going to correspond to the particles coming closer to each other. sorry, a force that attracts the particles to each other. And then if they get too close to each other, you can also think maybe there's something I can do to the potential function such that when they're very close, it's repulsive, right? And that would give you kind of this bouncing behavior that we're interested in having. So we'll talk about a special potential. That's the Lennard-Jones potential that we can use to model this type of behavior. So molecular just means that we're dealing with molecules and atoms, all right? And all these different types of interactions with potential fields involve some type of displacement, right, between them. And then based on those positions, we have forces. And someone was saying you have to keep track of momentum. So, it might look like, oh, they're really close to each other. Maybe they should be really repelling each other. But if they have a lot of momentum that brought them in contact with each other at the first place, right, the force may not have enough oomph to cause them to start going the opposite direction yet, right? But it can cause them to decelerate and then eventually go the other directions. Right? And this will be more clear as we proceed. So one way that we have to describe the interactions is by using kind of what we call pair potentials. So this is essentially saying we can have these different sets now of particles, not just one and one, although we're primarily just concerned with modeling 2 or 3 in the class for the lab and the post lab. But the idea is that these potential energies, right, are going to be acting between particles. And, if I have, let's say, this particle right here, I'm going to have, the particle over here acting on it. I'm going to have a particle over here acting on it. And if there's attraction between both of these, right, I'm going to have a net vector that might be going in between in this way. Okay. Again, we're interested in the kind of negative of the potential or negative gradient of the potential to be able to calculate these forces. And the dynamics are going to be affected by the distances. They're also affected by, as someone pointed out, again, momentum that they might have, or the initial conditions, the initial velocity as you're exciting the system. Nonetheless, these pair potentials are going to be able to dictate what's happening with the dynamics. And we also want to make sure that, well, maybe not make sure, but we have to consider that if the forces are not very large and you compared to the MA components or the mass, right, then they're not going to do much. Okay? But if you have some type of significance in terms of the forces with respect to their mass and acceleration, then we'll be able to see interesting behavior. Now, collisions, all right, we said, well, if you have just gravity, it's always going to be attractive. So how can you get a repulsive bounce? That's actually very hard to do with just gravity. You have to do something else. And yeah, you have the bouncing wall, and that might be one approach to it. Nonetheless, gravity by itself is not going to be able to handle this situation. You can have springs, all right, and they can bounce away from each other, but if the springs are not cut, it's eventually going to come back. Electrostatic forces, as we were discussing, they can be either attractive or repulsive. And there could be some adhesion that you're trying to model between the particles. Nonetheless, unless you flip the potentials, you're kind of stuck, literally, okay? If they're already attractive, they're going to continue to be attractive. And the intermolecular forces, those do allow you to have this bouncing off behavior. Okay. Oh, is there a question? Does someone have a question? Welcome to comment if you have a question. All right. And intermolecular forces can also be considered to be what we call van der Waals interactions. Okay, so an engineering accounting question. How do we keep track of all these particles? Okay, even if you have two particles, right? And we've already done this kind of in a sense, right? When we did the orbital mechanics, you had at least, okay, I know where the Earth is, and I know this thing is orbiting around it, the satellite. When we had the bouncing balls, those that's kind of one object, and even pickleball still kind of one object, but we do have the prescribed normal vectors and and a location on these different walls, on these planes that the particles are interacting with. So we have some idea of how we can keep track of like a single moving particle and the boundary conditions, right? And the simple way to keep track of the particle was to create these containers where you have the x position, the x velocity, the y position, the y velocity, the z position, and then the z velocity. So that's one approach to doing this, and we can store this information, like we said, in the containers. Now, if we have these kind of objects that we've been discussing, this is a nice approach, right? X's, Z's, velocities, mass, which has been conserved and continues to be conserved in our case. And we can, say, all right, we have some potentials, and this is what we've kind of been doing up to this point. So this would be object oriented. It's not the same thing as object oriented programming, right? But it's the actual objects are what we're tracking and keeping their properties stored, right? So we treat each particle as an object. That, though, you can begin to think would be kind of tedious if you start to have lots of particles. All right, so we will introduce another way of doing it. Okay, and this is very creatively called non-object oriented approach, or non-object orientation. And this is kind of how it goes. You have these positions that you can describe with column vectors. Or, they don't have to be column vectors, but okay, they're column vectors in this case, right? Some type of array, some type of vector, where the x now is the actual component, all right, of in that direction, and the subscript number is the number of the particle. It's its identifying particle. Then we can keep a track of the y's, and we can keep track of the z's as well. Okay, these are all things that we can keep track of, and so you have the number of particles in your system is going to be equal to the number of rows that you have in these vectors. When this is pretty straightforward, right? It doesn't necessarily tell us what's happening with the forces and things, which we'll describe in a second, but it's also a nice way to kind of keep track of the velocities, and you have kind of these three column vectors. Any questions up to what we've talked about at this point? Any questions? Okay, there's something in the chat. All right. Okay, there was no. But any questions? So these are just the locations of velocities of all the particles in the system. What gets to be clever here is that we can think of using matrices to describe the interactions between these particles. So we can think of having what we call unique base pair interactions. What does this mean? It means that if, for example, we want to think of, and we're thinking in Cartesian coordinates now, we're thinking of the forces in the x direction. And of course, these would be dictated, right, by the potential fields, right, and the negative of the gradient in these potential fields. But we can think of like, this is just going to be all the forces in the x direction. We can think of how each one of these particles interacts with every other particle in the system, okay? And we have here now fx11, and we have an fx22, fx33, and we go on and on. These subscripts are saying, what effect does one particle have on another particle? And if so, I have fx sub 1, that's just saying that 1 is interacting on itself, okay? Now, in this world, I can say, oh, I can interact with myself. That's very nice. In many cases, though, in a lot of cases, in fact, you're not, the particle is not going to, the gravity of the particle acting on the gravity is not going to cause there to be a force acting on that particle. So what you'll often see is that these are going to be, these will often be zeros. Okay, so this, if I don't knock over my screen, right? So these are going to be zeros because as much as a particle or I might like myself, I'm not going to be contributing a force on myself. Then we have the opportunity to think of what is particle 1 doing to particle 2, and what is particle 2 doing to particle 1. All right. So now this was a column vector, but we're kind of introducing another column vector. And we're going to end up getting all the fx, right? So all the forces in the x direction on these individual particles by thinking of all these interactions. Does that make sense? So if I have also a third particle, right, then 3 can be causing something to happen on 1, and 1 is also having something happening to 3. If I have also 2 and 3 particles, right, they're also going to be interacting with each other. So how is particle 3 acting or affecting the force on particle 2? How is the particle 2 affecting the particle 3? And you get through this and you say, oh, we can keep this going. We can keep this going and going, all right? And we can also do this for the y component and for the z component. Okay, does this kind of make sense? So essentially what you're seeing here is that the Newton's third law, okay, so like this is, an example of Newton's third law, where every action has an equal and opposite reaction, okay? Because we know that these particles are going to be acting on each other. And if it's, gravity, or if it's an electrostatic force, if it's a spring force, if it's an intermolecular force as well. Okay, so this is just another way of accounting, right? We've talked about it before. We have to be good accountants when we run simulation, keeping track of everything. Any questions up to this point? Okay, so the next slide is just a reminder. Oops, okay, that's me writing over my own writing. Okay, we'll just say, all right, yes, that was still in there, but I just wrote it manually. This is Newton's third law. Okay, so now the next slide is saying, all right, we can use what we already know. This is the same slide from, I guess, our second session together, where we talked about the velocity relay integration algorithm and how we can use it to be able to figure out what's happening in one time step, and then the half time step to position and velocity, and then figuring out what's happening with velocity in the next time step. All right, so we have this updating, we have this very important step number 3 where we're using the potential, right? So we have some type of potential function that we can take the negative of the gradient of, and then calculate what the force or the acceleration, right? So the force on the object might be, divide by the mass, and then you get the acceleration. Okay, so we've done this now a few times. When we start to look at setting up the base pair, the unique base pair interactions, here is what it looks like in MATLAB. Okay, so we're going to have 2 for loops. We're going to have a for loop where we go through one subscript, right? So we had like fx11 and fx12, fx12. So this would be like the first subscript, right? So if I had, if I had like f, let's see here, I'm just going to go over myself here. But if I had f, right, like this, x, I would maybe have f, x, sub, so I have f sub x sub ij, okay? And so the i's are going to be in this, whoops, I'm going to knock over my stuff here. And then this would be the j's. Now, you may be wondering, why don't I just go from 1 to n and from 1 to n, okay, for the j's? Well, if you looked back at what we were describing in the previous slide, there was this kind of interesting pattern that was emerging where we would be getting zeros essentially in a lot of these interactions. And in this case, when we do this implementation, we're using kind of a set of pairs, okay, so that the main diagonal has zeros in it, and then everything to the left also has zeros in it. Okay, so we're looking at interactions between what we'll call unique particle pairs. Okay, so we don't want to double count essentially. Okay, and on the main axis, on the main diagonal, sorry, we already said that a particle doesn't affect its own self. Okay, so what we're doing is we're essentially going through and looking at how these different particles interact with each other, and we're looking at how they're going to exhibit forces on each other, right? So, for example, this part of this matrix, this one would be like corresponding to I equals 1 and j equals 2. All right. And we are going to be keeping track of, okay, this is how, this is the force that's going to be exerted on particle 1. All right. And I'm going to be making sure that I don't then accidentally count what's happening with particle 2. Like I'm I'm not keeping track of the particle 2 at this point. What's acting on that? Okay, if that makes any sense. Is there a question or comment? Okay, yeah. What's the practical limit of this method? Right. So essentially, that's a very good question. Practical limit is when you try to model big things. And what is big? Okay. So if I want to model, for example, how temperature flows through a solid, so people know, the question is, what is the practical limit of this procedure? Yeah, it's when you model big things and you really don't care about the minuscule behavior. You care more about what's happening at like the, at the micron, millimeter, or whatever the relative scale might be. It doesn't make sense to have, a an Avogadro's number of molecules that you want to be keeping track of for your behavior. Okay, so that's a good question. So we're going to be keeping track of just a couple of particles today. All right, so this is like if I want to see how electron flies off or how they're attracted to each other, how they interact with each other. This is where things can be kind of useful or interesting. Okay, good questions. Now, um, let's do a little bit of demos, a little bit of demoing for what this means with colliding electrons. And you're like, what? Colliding electrons? Okay, yeah. So essentially, what we're saying is here is going to be one electron, okay, and here is going to be another electron, okay, and we're going to use repulsion. So we could say, okay, let's say that this one has a positive charge. Okay. And this one maybe has a negative charge. Like that. Okay. And so well, sorry, actually, that would be attraction. If one is positive, one is negative, then they'll be attracted to each other. But if I want repulsion, then I'm going to have like two positive charges. Okay. So you're like, oh, well, that's not very interesting. Well, it could be interesting. If I put these particles really close to each other, then they're going to want to separate. Okay. And so that's one way to look at it. When we think of colliding electrons, though, what we're going to do is we're going to prescribe some velocity. So we'll have some v1, and that's going to cause this particle to march along, and eventually it's going to get very close to this other particle. And when it does that, because of the repulsive electrostatic forces, it will cause this other particle to then go off like this. And this will be some V2. Okay. And I guess, we're saying if everything's conserved, the V2 should be kind of like that. And this other particle can kind of stay there if it's an elastic collision. Or it will get bounced off a little bit as well. All right. In the chat. Okay. You want some more explanation of the IJ thing? Okay. So just coming back to this, we're going to set up this pairs matrix. All right. And that's going to be what is for the conditional. So if you get unique base pairs, all right. So like, let's say that you get a 1, 2 or a 1, 3 or 1, 4 or 1, 5, right? That would be all unique. Or you get in this case, this would be like a 2, 3, a 2, 4, a 2, 5. Okay. These are unique. I can keep track. So, right, I don't need to do like 2, 1. I don't need to do this one over here because I'm already going to account for it when I do it when I come over here, right? So, the unique. So if I just wanted my pairs, right, then what I would have is I just have like, ones over here as well. Okay. Right. But I'm using this pairs matrix with unique pairs just to decide with a Boolean, right? So if I'm at a unique pair as I march through this matrix, then I will begin to do some work. Okay, I'm going to begin to think about, okay, what is the distance between these two particles in the x direction? What is the distance between these two particles in the y direction? Then I can figure out what the magnitude of the distance is between them. And if I know that, then I can figure out what the the distance vector looks like. All right, that would be the big R. And divided by the distance, that will give me a unit vector. All right. And then I can figure out the force between those two particles. Okay, the force between the ith and the jth particle. And then I can say, oh, for particle 1, that is going to lead to some force acting on it. Okay. And that force, that magnitude this is a scalar. This is a Coulomb. This is a function that you'll be given and create. and that will give you the force. All right, that's just a magnitude, scalar, and then we know that it will be happening in the direction of this radial vector that we have, right? The radius vector is going to determine, okay, if they go, if I have this and this, it's going to determine, okay, which direction that force is acting. So I can figure that in the x direction, I can figure that in the y direction. And then for the other particle, its corresponding other particle, I can figure out what the forces are acting, if the equal and opposite forces, all right, that you're going to have acting on it in that direction. So you see that it's minus minus here for particle one, but since it's happening in the opposite and equal direction, I have a minus minus here. All right, and it just keeps going through this unique pairs matrix. Thank you for asking that question. There was another question I think that kind of broke up some of the flow of what we were talking about here. So thank you for asking me to go back to that. All right, so what we're going to do in MATLAB is essentially look at how these particles, how these electrons, they interact with each other. And what you're going to see is that like we can, maybe we have like a red one. Okay, I know this is like, now I'm just like, okay, whatever. And I have like, I don't know, a green one. I don't remember what the colors are actually. It's actually probably blue, red, green, because that's how MATLAB often works. And then when they, we're going to see what happens to these particles and how they move. So let's go. I hope that MATLAB will work for us as we do this. All right. So here we have, if we go to the two colliding electrons, and I think I might have to go up a level. Okay. Yeah. All right. Here we go. Just to make sure, because I need this F Coulomb function to be in the same directory. I mean, often MATLAB asks you when you hit Control Enter when you run it, what that is, or to change that directory. And I do suggest not adding to your path, but just changing to the appropriate directory. So I hit Control Enter, and it's running along now. And there are two particles involved here. They both have the same charge. They've been put at negative. They both have a small mass. Okay, and what we should see, all right, is this is particle one, blue, and then it hits particle two, red. Particle one goes this direction, and particle two goes this direction. Now, this is not what I just drew, really. I mean, I was like, well, they're going to keep. Why do you think they don't continue in the same exact direction? Or why did one not just stop? Like, why is there an angle at which they're separating? Okay, and that angle is pretty close to 90 degrees. In fact, okay, this is the MATLAB scripts doing this, and you'll in the lab you'll be able to do that. But why would they like bounce off at an angle from each other? Any ideas? Chat. So think about if you're playing billiards and you don't want, okay, there's a chat, all right, okay. Okay, because they started at, okay, it's not head-on collision. Okay, right, okay, exactly, right. So let's play around. I don't know if this is going to work exactly, but let's see if we can play around a little bit. So if we, okay, if we start with them aligned, let's see if they end up going in the same line. What I've done here, and what you'll do is they're actually offset. Okay, so these are the x's, right? So now this is actually a column vector because it has the apostrophe and it's transposed. Okay, so the position of the first particle is minus 3 millimeters, comma 0. All right, that's in millimeters. Okay, so that's that. The position of particle 2 is at 0, and then a little bit above 15 nanometers above. Okay, so what we're saying is that they're not quite aligned. If this were particle 1 and it's coming in, and this is particle 2, it's like actually just up there. And so as someone put in the chat, it's not a head-on collision. So if you're playing billiards, right, and you're trying to get a ball in a pocket, you don't want to typically line your cue right in, put them both, or, you don't want the both to like go straight and follow each other, right? Because then you'll get a scratch. So what you might want to do instead is try to hit the ball at a slight angle, right, to be able to get it to go off. Or, right, you can put a little backspin, but we're not putting backspin in this, right? To make sure that the ball doesn't follow it directly into the pocket, right, to commit that scratch. So let's see what happens if we change this now to 0. So now the x's are different, right? But we're putting a velocity in the x direction. What is the velocity? The velocity is it's pretty significant, okay? It's 10 to the 5th meters per second, all right? So now if they're aligned, what will happen? Okay, so we're going to run it again. Okay. There it comes in. And boom. All right. This blue particle actually kind of stayed in place. And now the red particle is going forward. Okay. So that just that small misalignment is causing there to be issues. Now, what's the angle? 180. Why is the angle 180 degrees? Well, it's possible, right? And this is what's happening, that this angle, and I know it is, it's not just possible, it is, it's calculated based on the velocity vectors. So the particle 2 is essentially captured all the momentum of particle 1. And its velocity vector is to the right. I guess I'm whatever. It's okay. Please do the mirroring in your head. But it's going this direction. The particle 1 is stopped, and so or actually it hasn't quite stopped because it's repulsive. So actually that particle 1 can go slightly backwards. Okay, so that they're actually the velocity vectors are going. One's going this way and one's going this way, and they're 180 degrees from each other. How do you see this? If you go down, you'll do this in the lab. You can look at these velocity vectors or calculate, right? So remember, the simulation is keeping track of these velocity vectors. And what we're saying is that we want to be updating them, and then we want kind of these final velocities. All right. And so this is where, and remember, this is maybe a little bit confusing, right? You're like, wait, US1, VS1. Yeah, that actually is keeping track of what's happening in particle 1. That is not a time step in the parentheses. That is particle 1. This is particle 2, US2, VS2. These are the U's and the V's, right? These are the U's are going to be the X components of velocity, and the V's are going to be the Y components of velocities. This is just simulation in 2D. All right, so the question? Right. Okay, are they repelling each other or just colliding? Very good question. As you bring two particles together, as you bring them closer and closer, right, the electrostatic force gets extremely high, right? And that can be thought of in terms of the negative of the gradient of the potential, all right, as well for electrostatics. So you've got a lot of speed, all right? We got this 10 to the 5th meters per second coming in, and that speed is not really that affected by the repulsion force, but they are repelling each other constantly in this problem, right? Because they have the same charge. When they get extremely close to each other, that is when they have a very strong repelling force, and that's what causes them to look like they collide and bounce off each other. But they're not actually, they're not actually, quote, colliding in terms of how we thought of the wall, all right? Thank you for that question. But anyway, so back to this. If you look at V1, this is the velocity vector for the first particle at the end of the simulation, right? Because I'm plotting everything, but if you look at this, we don't have containers that are keeping track of things in time. We are marching in time, right? You have your dt, you have the number of iterations you want, but this problem is kind of unique in that we're just plotting every single time, and that is how we are tracking the position of the particles visually, okay? So at the end of the simulation, wherever the last simulation was, the v1 is going backwards, right? Just slightly. And if I want to make it a unit vector, then I can say it's v1 unit. All right. And it's really just in the -1 direction. Similarly, the second particle, v2, right, it has, look at this, it has a velocity that is pretty much 10 to the 5th meters per second. All right. And then it has 0 in the vertical direction. All right. And if I want to look at the unit vector of this, I can plot it like this. All right. So this is why the determination, this output that we had, angle 1, 2 is 180 degrees. Okay. And you can use the arc cosine essentially, right? Because if you dot product these, you can use the arc cosine to be able to figure out what the angle between them is. And then we convert it to degrees. And that's what you see spit out here. Okay. Now, you've brought up an interesting question, though, in that are these particles really colliding, or are they just going through each other? What happens if, and let's put in an offset again. Let's put in this 15. All right, we put in this offset again. What happens if we have a situation where the time step is too large, right? Because this is something that can happen is, okay, I'm keeping track. And remember, we had to, and when we were doing the collision with the wall, if the time step, well, you know, we had to figure out, are you in the wall or out of the wall at each time step? In that case, if you were in the wall the next time step, then we figured it out. But here, you could go, if the time step's too large, you'll go through the particle, and then you'll be far enough away, and you're just repelling each other, but it's as if nothing happened. Okay, so let's see what we can do here. So if we come in, we go to the time step, and this is, you know, very small time step, 0.1 picoseconds. All right, let's say we do 3. All right, that's a new time step. So 3.3 picoseconds instead of 0.1 picoseconds. Okay, we run this, and we should see the motion, okay? And it moves along, and it still interacts. So that's okay. Okay, so that's fine. What if we do, I hit Control C. What if we do something like a picosecond, 10? Okay, wait for it. Okay, still okay. All right, let's do like 10 picoseconds. Okay, I hit Control C. Okay, so we're still getting the behavior. But now you see what happened. The particle went through the other particle, right? The next time step was so far, it caused it to go so far that that instead, yes, you had the repulsive. What's going on? I must have run it again by accident. It went through the particle because, or the collision behavior wasn't really simulated because it just didn't develop a high enough repulsion force while particle 1 was still just to the left of particle 2. Okay, it developed that repulsion force because we're seeing a significant shift in particle 2 now to the left and not to the right. It developed that repulsion force, but it developed it right after it went past it. Okay, because of too large of a time step. So this is kind of a fun exercise, I think. I mean, I think it's fun. Maybe you're like, this is boring, but of how you can think about time step is is having an effect on these colliding particles, and in the simulation that we're performing, it's interesting in terms of thinking about, okay, how their relative position and their velocity also affects how they're going to interact and how they're going to bounce off of each other. Okay. All right. Any questions? Okay. Great. So what we're going to do now, though, is discuss intermolecular interactions in the next 20 minutes. So here is kind of a thought experiment. We have two balls that are far from each other, and they don't really exert any forces on each other, right? And you can think, oh, yeah, that could be true of gravitational field, that could be true of an electrostatic field as well, right? We know that these potentials have kind of this inverse distance property to them. Now, when they are brought together, okay, in some distance, okay, some specific distance, they have some attractive force between them. All right, so this could still be kind of largish, you could say, but like when they're really far apart, they don't interact. When they get to some distance, they do interact, and it can be attractive. And then so this attractive force, say the initial velocity was 0, this attractive force is going to get potentially bring them closer and closer to each other. But then, as the balls begin to overlap, okay, there's a repulsive force. And you can kind of think, well, that makes sense. I mean, if I have two rubber balls and I push them into each other, they're going to, you think we're mechanical engineers, they're going to bounce off. But this is not a material model, right? Not a bounce off a wall model. This is an interaction between essentially potential. It's just using potential fields essentially. Okay. So what does this look like? And yes, this is what we call a Lennard-Jones potential. This is one way of modeling this behavior. Okay. So here is what Lennard-Jones said many moons ago. All right. So this is in the 1930s. Atoms of a noble gas interact via potential, which an attracting van der Waals force balances a repelling force, which results from overlapping electron orbits. So, if the orbits are not really overlapping with each other, there's this kind of attractive intermolecular force, that's a van der Waals force. But once those electron clouds or orbits get on top of each other, they really don't want to be, they really don't like that, okay? So so you're like, okay, so the force has to flip. Well, do you remember that the potential field, when we had gravity, okay, this was for gravity, it kind of did something like this. Okay, so this is potential. This is the potential for gravity. Okay, and you can kind of see, yeah, it's always attractive, and if you get really close to each other, it gets very attractive. Okay, so that's like, I don't know. Well, I guess I've thought about this before, and I mentioned it before. Like, two people see each other across the room, and they're attracted to each other, and they just gravitate toward each other, and they end up liking each other a lot. Okay, and there's just such an attractive pull between them. Okay? What the Lennard-Jones potential is saying is, nah, not exactly. All right. Yeah, you can get really close to each other, right? So let's say that it looks something like this. Okay, this line right here is what they're talking about, where this is behaving like gravity underneath the horizontal axis. All right, and then you get to some point where the sign, right, it actually flips. All right, so the slope is, I mean, if you're going from this direction, right, the slope is always positive if you're going from left to right. But if you're coming this direction, the slope would have been negative, coming from right to left, whatever. But the slope flips and actually goes above the horizontal axis. So you have this attractive, 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 but then once those electron orbits begin to interact, it gets extremely feisty and angry. They get upset with each other, and it's like, you've invaded my space. I'm going to push you off, and I can push you off pretty hard. Okay, with the way this potential is working. So there are some terms that come in here. Okay, and the function, this potential function, can be thought of in terms of a 12th power and a 6th power. So sometimes this is called like the 12-6 Lennard potential function. The potential is V. The epsilon is the well depth, all right, and a measure of how strongly the two particles are attracted to each other. So if your epsilon is higher, okay, this will be deeper. The sigma, all right, this is when the potential hits the 0, all right, and that's kind of that's interesting. That's where the potential energy, right? So if it's not stable there, but that's where the potential energy would be 0 between them. And the determination of how close these two non-bonding particles can get, it's going to be determined by what's called a van der Waals radius. And this is it's kind of like that. It's considered to be half the internuclear distance between non-bonding particles. Okay, so a little bit more on this. That this there's a minimum distance, okay, where they can essentially interact with each other, and that is given by, well, they interact. No, this is a radius. Okay, if you had like two molecules that they're kind of happy with each other, they have that you have a minimum right here where you kind of in that, that we talked about this epsilon, right, that depth here, but you have this distance here, okay, where that Rm is dictated by 2 to the 1/6 times sigma. All right, so you can kind of take some derivatives, set them equal to 0, and figure out this minimum. Okay, now the force associated with the Lennard-Jones potential, right, also has to do with the derivative. Okay, right, the negative of the gradient, and we can think of now not electrons themselves, but we can think of the some molecules that are involved. Okay, and this still has a conservative scalar potential. This is the Boltzmann constant. This is the kind of the sigma, and then Rm, which is like, well, it's the 6th root of 2 times the sigma. It's like 0.44 nanometers. This is where you hit this Rmin. The attractive force can be given by this negative of the gradient, and this is what you get here. Okay, we can have MATLAB do all these calculations for us and be able to calculate what the force is at a given location. So this is not really any different than what we just described with the electrons. What is different is that unlike the attractive or repulsive behavior between electrons, that's always attractive or always repulsive, right? Even when they went through each other in that previous example, they still repulsed each other. So because they had the same sign for the charge, same sign. So what you have here is a situation where because of the way this potential has been designed by Lennard-Jones, then we have the sign flipping on the force. Okay, so here is a MATLAB plot, okay, for the Lennard-Jones potential between two atoms, and here is the force, okay, and you can see the force when the distance between them is, quote, large. Okay, so this is still like 10 angstroms, or like well, this is 10 times, so this is like, this would be like, yeah, this would be 8 times, or let's say 10 times 10 to the minus 9. Okay, so that's 1 nanometer, but like this would be like 4 angstroms, whatever, coming up this way. 4 angstroms, 0.4, 4 nanometers, as we were saying. This is at these higher values, the force is positive, and that's going to cause there to be attraction in this case. But once the electron clouds overlap, you get an extremely negative force. And that causes there to be lots of repulsion. Okay. Now, what could happen with time step? We just saw it, right? If you use let's say that you have like a really small velocity, okay, like they're initially very small, and you're starting here, and you have really nice small time steps. Okay, you can just march along, march along, march along, march along, march along, and then you might go through here a little bit, but you're eventually going to sink into that intermolecular distance. That's the square root of 2, or not, it's a 6 root of, right? It's a 6 root of 2 times the sigma, right? That's what this was. And this is non-dimensionalized, right? This is just one, this is R over sigma essentially. So this is coming out somewhere over here. That's the Rn. So that's what you think. Okay, low initial velocity, everything's happy. I can eventually settle. If you fire with a lot of velocity, though, this molecule at another molecule, though, you're going to expect to see a bouncing effect, right? Because this involves this collision behavior, which is what we saw even with the electrostatic case. As long as you're, but that again, it's a balance of time step and a balance of what the initial velocities would be. If you have a large time step, and let's say you start off here again, and then you go here, and you go like here, and then you're like here, it's possible that your particles will shoot out big time. Like they could be really close to each other, like really nice and interactive, right? And they could get a little bit closer, right? And even though and then suddenly like they're in each other's space, and so then they just like shoot off from each other, okay? Like this, because you've gone way up on this. And the gradient here, the negative of the gradient of this potential function is going to be high. And that's what causes there to be extreme repulsion. Okay, any questions on this? So once again, any questions? Yeah, in the chat, feel free to put them there. Okay. Let me
just to show that effect and to give you.
Oh yeah, so that's Professor Singer, right? So there's some videos and stuff that you can that you can watch with Professor Singer. Okay. What I'd like to, I guess, talk about is some of the practical things that you're going to encounter when you do the post lab. All right. So the post lab, let's see, where is that? I didn't get to the research again. All right, because I guess I'm just too slow. I don't have the assignment here. Where I didn't put it in. Let me see if I can. And if anyone wants, I'll give you a couple seconds to like take a picture of yourself, and this can be your attendance. We're just using a white one because well, anyway, I'm just using a white one. Okay, let me see if I can find the assignment, and I'll bring it over to look at without revealing too much, I hope. Okay. So in the assignment, okay, so and I can share it. I can put it back up in a few minutes. All right. Here's the assignment. What's that? Yeah, you can turn the camera on and take a screenshot. I'll let you have some time in a minute to do this. All right. This is, so I guess maybe I can back up and say, this is maybe the most challenging unfortunately, assignment for the MATLAB stuff because there seems to be a lot of questions. So there's been some question. Can you be more clear in terms of the? I'm trying to be clear, and part of the class is to be able to kind of decipher and read. Like when it says deliverable, like that's a delivery. When it has a question, try to answer the question. I guess. But you can talk and converse. Like it's not just like the answer is A. Okay, it's not multiple. It's like these questions they're a little bit involved and they require some interpretation of the question. Okay, so you see that this lab 3, we're going to first focus on colliding electrons, and then the post lab actually is going to focus on colliding atoms. Colliding electrons are just going to be using the electrostatic potential function, but the colliding atoms will be using the maybe this will be better. Okay, they'll be using the Lennard-Jones potential. Okay, so there are going to be some constants. All right, and then you're going to put one particle 10 nanometers to the left of particle 2. Okay, and then particle 1 will have an initial velocity towards particle 2, and you're going to use a certain time step, and it's not going to converge. Okay, and it will shoot off, okay, or cause problems, or you might just see the particles disappear really fast. Then you want to reduce it, right? Because remember, what we're saying is that with the Lennard-Jones, where did it go? Where did it go? Where did it go? Here, okay. With the Lennard-Jones, if your time step is too large, like over here, you're just going to get garbage. Yeah, you're going to get something that doesn't make much sense. Like it could just go through, for example, all right, like it showed before. That could be that because because then it's calculating the distance. So if you just go through, then you're not going to do it. So you got to reduce the time step appropriately, and then you can get a behavior. All right. So we talk a little bit about what convergence means in the past, and that has to do with, okay, as I reduce the time step, so if I don't know the answer, right? If I know the answer, then I had to look at how I'm doing compared to that answer. But if I don't know the answer, then I have to look at, oh, as I decrease the time step further, I don't get any change in behavior, right? So the first one is about convergence. And it's just include a couple of sentences of text explaining which time step on the plot represents a converged time step and why. Okay, so you're gonna be iterating through time steps with this high velocity. Now, we're going to talk about bonding. So this is 1 with high velocity. Then 2 is going to be about particles that bond with each other. What does bonding mean? Bonding means that you're going to be in a situation where you stay somehow close to this distance, all right? Or that they bounce off of each other, okay? They could move together, that's fine, but they don't repel each other. You've got an initial velocity small enough that they stay in proximity to each other and they oscillate. If I have a high initial velocity and I'm converging, then I could very well just get shot off, right? And I get repelled from each other because that's what we have. You have a very high gradient. But if I go in slow enough, right, I bring them in close enough proximity, then they will oscillate and they'll vibrate with each other. It's a beautiful thing, okay? So I don't know what those comments mean, but so let's say that I've got my MATLAB, and we're going to look at the bonding. All right. And I want you to, kind of try different things. And hopefully you don't do exactly this one condition. All right. Um, and what you're going to see is here's particle one, the blue one. Okay. And my computer, oh, it's because, all right. See, this is because I didn't change. I had to change the directory. Now let's run it. Okay. So now we're in this right directory, so we don't get an error. Okay. So now particle one can come in. It's coming in nice and slowly. And then particle two was attracted to it. The red one was attracted to it. And then they keep on bouncing off of each other. You see, they're bonding. This is like a nice relationship. Look, we get nice and closer, but oh, let's separate a little bit. Okay. So this is what we want. This is what we're aiming to have for the second deliverable for post lab 2. All right. And I'm sure there will be some questions. So ask some questions in the chat, come to the office hours, and we'll try to address things. What have we talked about today? Well, we have not talked about my research in the past, but we have talked about how to further simulate interactions between particles. And we're talking about electrons and we're talking about atoms. We're talking about how to use different types of conservative scalar potentials. And in particular, we're talking about how to use Lennard-Jones potential for intermolecular interactions. So thank you for your time. I'll put this up. This is what you want to take a screenshot of for your attendance today. And I look forward to seeing you in person in a week from today, Thursday. Thank you for the notes. Yes, have a nice day, everybody.